Today we're going to introduce our third theorem of the year. Anybody think of any of the first two? Okay, EVT, IVT. All right, so let's remind ourselves of what those are. All right, IVT. Intermediate value theorem. Okay, one of the requirements of the intermediate value theorem is continuity. Intermediate value theorem doesn't work if the function is discontinuous. So this requires continuity. And it requires continuity on a closed interval, starting at A, ending at B. So we'll say A to B closed. And if continuity is satisfied on that closed interval, then the intermediate value theorem is going to argue opposite sides of the x-axis. If the endpoints of that closed interval are on opposite sides of the x-axis, then what has to happen sometime in that closed interval? You have to cross the x-axis at least one time. All right, and so that is the basis of the intermediate value theorem. So if, try that. If the endpoints, which are f of A and f of B, can be shown to be on opposite sides of the x-axis, so one is positive and one is negative. It doesn't matter which one is which as long as you have one of each. Okay, so if you can do that, so you literally have to show, you've got to find the first endpoint, find the second endpoint, show that they're on different sides of the x-axis. Okay, then the IVT guarantees the presence of an x-intercept, or a zero, or a root, all those words. I like the word existence better. Guarantees the existence of at least one root within A to B. There could be more, or it could be multiple, but you're guaranteed to have at least one. These theorems all serve to guarantee the existence of something. The extreme value theorem did the same thing. We talked about that 2 days ago, the EVT. It also has the same requirements. And so it requires the same thing, continuity on a closed interval. And we'll again call that closed interval A to B. If that's true, if you have a continuous function on a closed interval A to B, the extreme value theorem guarantees the existence of at least one max and at least one min. Within that interval. And it's not one max or one min, it's one max and one min within the interval. Okay, so we're ready to do the MVT, the mean value theorem. mean in math having the meaning of average. So that gets us to the third one. And so this is the MVT, which stands for mean value theorem. And this is the first one that has a different requirement. Not only does the mean value theorem require continuity, like the others, but because we're going to be talking about average, we're going to be talking about slope. And if we're talking about slope, we're talking about differentiability. And so not only does it require continuity, but it also requires differentiability. Both things are required within the closed interval, a to b. In other words, there can't be any asymptotes, there can't be any jump discontinuities, there can't be any gaps, there can't be any removable discontinuities. Those are all the continuity things. But what else can't there be within to make it differentiable? Can't be corners, can't be cusps, vertical tangents. Those are the three things. So this one has a stronger requirement. Okay, no asymptotes, no gaps, no removables, no jumps, no oscillation, no corners, no cusps, no vertical tangents. Horizontal tangents are fine. Okay, so none of that. If all of that is satisfied, then the mean value theorem will guarantee the following. Guarantees the existence of a value c, little c, such that the following is true. F prime of c, what's f prime of c mean again? I'm going to tell you what it's equal to, but what's f prime of c mean? The derivative at c, right? What does the derivative mean? The slope. So the slope at c is equal to f of b minus f of a over b minus a, which is the slope connecting what two points? The endpoints, a to b. Okay? So basically we're saying that the slope at point C is equal to the slope that connects the endpoints. And if two slopes are equal, what do we call that? Parallel. Okay? Two slopes are equal, we call that parallel. If a line goes through one point, what kind of a line do we call it? Okay, or maybe ask a tangent line, okay? If a line goes through 2 points, what do you call it? A secant line, right, okay? And so we're talking about here, the slope at C is equal to the slope connecting A and B. And if the slope at C, which is a single point, is equal to the slope connecting A and B, which are 2 points, then we can conclude that the tangent line at C is parallel to the secant line through A and B. So sometimes it helps to picture what's going on here. Okay, the tangent line at some C, you're guaranteed that this will exist somewhere. All right, so I'm going to draw you just a sample function and give it two endpoints, and the endpoints are called endpoint A and endpoint B. Okay, and you say, well, does this satisfy the requirements of the mean value theorem? Is it continuous? Yes. Yes. Is it differentiable? Yes. Yes. Okay. So, if those two things are true, then I am guaranteed to be able to draw the following. I should be able to draw a secant line that connects these two. And I should be able to find at least once, if not more than once, a point C somewhere in that interval that's parallel to that, whose tangent line goes right in the same direction. And if I'm just eyeballing it, it looks to me like I could maybe find one right about here. Okay? Is there any more? In this one? Yeah, I think maybe, well, if I were to estimate, maybe about right there or so. And I happen to find two of them. But you're guaranteed that there will be at least one. There might be multiple, but there will be at least one. That's the crux of the mean value theorem. Okay, the mean value theorem guarantees the existence of this mystery point C. This one I happened to have C1 and C2. I had two of them. Where the derivative at that point is equivalent and exactly equal to the slope that connects the two endpoints of the function. All right, so let's practice that on some actual functions. Okay, let's look at the function x cubed minus 4x on the closed interval from -2 to 2. Now you don't have to draw this, but sometimes it's helpful to think about what that looks like, but you don't have to draw it. We do know that it satisfies, I'll check the checkbox, it is continuous. And I'll check the checkbox, it is differentiable because it's a cubic. Therefore, f prime of c is going to be f of 2 minus f of -2 over 2 minus -2. And so then I just do the math to solve for what that f prime of c would be. So first I need to find f prime. F prime is 3x squared minus 4. So at c, that would be 3c squared minus 4. Okay, that's the derivative value with c as the variable. And on the other side, I need to figure out what f of 2 and what f of -2 are. So the endpoint f of 2, if I plug 2 into the function, what do I get? I do, I get 0. And if I plug -2 into the function, what do I happen to get? I also get 0 over 4. So basically this comes down to the fact that 3c squared minus 4 must be equal to 0. So c squared is 4/3. And so c is the two values, the plus or minus square root of 4/3, which we could simplify as the plus or minus 2 over the square root of 3. So there happen to be two values, both of which fit within the interval. And if I were to draw this, I should be able to figure out that a secant line that connected the endpoints of this graph would be parallel to a tangent line that I created at that graph. Okay, let's try another one of those. Let's take the simple parabolic function x squared on the closed interval from 0 to 2. So we can be assured that this is continuous, and we can also be assured that this is differentiable, which means that the mean value theorem, f prime of c, can be shown to be equivalent or equal to f of 2 minus f of 0 over 2 minus 0. F prime at c, well, the derivative is 2x, so at c it would be 2c. The endpoint f of 2 is 4 minus 0 over 2 minus 0. So 2c is 2, so c is 1. So I only have one place where this happens. So for this one, I would like to demonstrate the drawing of how this looks. Let's find the tangent line, and let's compare it to the secant line. So the tangent line is going to be at c equals 1. The point would be 1, 1. The slope would be the derivative of that, which is 2 times 1, or 2. And so the tangent line will be y minus 1 equals 2 times x minus 1. There's my tangent line. My secant line will go through either the point 0, 0 or 2, 4, either one. You'll get the same thing either way. The slope will also be 2. Which means that the secant line works out to be y minus 0 equals 2 times x minus 0, or simply y equals 2x. So now let's take a look at the drawing. This is a parabola. The parabola goes from 0 to 2 on the x-axis, and its endpoints are at the origin and at 2, 4. The secant line I'll draw in green. Okay. The secant line is the line that connects those two endpoints. It has a slope of 2. The tangent line I'll draw in yellow at the point 1, 1. And its tangent line is perfectly parallel to the secant line. And that happens just once, and it happens at the point 1, 1, or the c value of 1. So sometimes you'll just be asked to find c. Other times you'll be asked to draw the representation of what that means, and actually to figure out the tangent line and the secant line. All right, so this mean value theorem can be used to prove that you deserve a speeding ticket. Okay, let me show you how. Have you ever driven by a sign that says speed monitored by radar or by photo, like airplane, like if you're way out in the desert, sometimes you see like speed monitored by aircraft? Okay, all right. So how do they do that? How do they monitor your speed by an aircraft? They take 2 pictures of you, okay, at a certain interval of time apart, and then they can prove whether or not you were speeding. So let me show you how that works. All right, so let's say that a car's position changed 352 feet in 8 seconds. The mean or average rate of change the mean or the average rate of change over those 2 positions would be 352 minus 0 over 8 minus 0. 352 divided by 8. Okay, we'll check that out. 352 divided by 8. Okay, we get 44 feet per second. So let's convert that into miles per hour. Okay, remember from your your unit conversion stuff from your science classes, hopefully how to convert. If you've got 44 feet per second, how many feet in a mile? Very good. 1 mile is 5280 feet. All right, and so we put the 5280 feet on the bottom so that the feet units reduce. We need to also convert this into hours. And so we need to convert seconds into minutes and then minutes into hours. And so we have 60 seconds in a minute. And we have 60 minutes in an hour. So if we convert this feet per second into, we need 44. Look at the units here. The feet reduce, the seconds reduce, the minutes reduce. We're left in miles per hour. So we're going to have 44 times 60 times 60. So we'll end up with, whoa, almost 1,58400 over 5280. The units on that are miles per hour, which works out to be only 30 miles per hour. Therefore, the person was not speeding according to whatever the posted speed limit was.